Right, hello everyone, my name is Parth.
And I'm Arunan, and we're both the Micromouse leads for this year. So what is Micromouse? So we taught students how to make an autonomous maze-solving robot from scratch. And the skills that we unlocked for the students are being able to power your Micromouse, utilize motors and encoders to move throughout the maze, and also to be able to track how you're moving throughout the maze. PID control, so that you can accurately move throughout the maze and keep track of those movements. And IR sensors to know where there are walls and to not run into any of the maze walls. And then also schematic and PCB design, so that way the students can create their own custom designs and also be able to select their own components in order to assemble the whole robot together. And then we also taught them flood fill, the maze solving algorithm, so that way they can actually navigate the maze using the sensor data that they can accumulate about the maze from their various sensors.
So yeah, other than all of like the things that we teach them, like what you guys actually want to see in the project showcase is like the end result. And in our case, the end result is the All America Micromouse competition that we held last weekend, actually in this very building, just like a few steps over. It was a very how do you pronounce it? Oh, okay.
Yeah.
It was kind of a massive event. We had 14 teams participate from schools from across the country. Most of the schools were from California, so we had schools like UC Irvine, UCSD, and a bunch of teams from UCLA as well. But we also had teams from outer state, like a team from UChicago and a team from Arizona State University. So overall, it was a pretty successful event. It was really fun to organize, and you can see in some of the pictures over there how big the actual maze was. Unfortunately, we couldn't bring the entire maze because there's no space to set it up, but we did bring a smaller one that you can see outside during the demonstrations. Yeah, this year the maze was actually solved by a good number of teams, unlike last year, so it was a massive success. And yeah, here's just some more AMC photos. And yeah, now we have a couple of our teams from UCLA present about their mouse. First is Michael.
This is me, by the way. Just prior to today, I had a beard, and now I have no beard. People are giving me funny looks that know me. Okay, I'm presenting on my thing. I didn't know how to be so detailed. Like Sanjit was like, he gave like all the information that you could ever want. I just discussed my journey. Wrong way. Yeah. So for context, in fall, I was having a rough time because basically nothing was going well. I kept getting stuff that wasn't working for my rat, which is my tutorial mouse. And so by the end of the quarter, my rat didn't work. It couldn't even drive forward. So that was not good, and it destroyed my confidence. Yeah, I just said that. Wait, hold up. My slides were updated. Okay, there we go. Yeah, and so basically, for my my own mouse design, I was like, okay, I need to be able to do the normal stuff before I can do some advanced stuff. So I basically just made the rat again, but I still decided to make the schematic and stuff because I wanted the experience of making the schematic and the PCB design myself. And so yeah, basically all the parts I used were exactly the same. It's my goal was just to finish the maze, which I succeeded, by the way, so I'm goated. But yeah, and regardless of the time, so here's my mouse. My greatest troubles I faced was the PCB design at the beginning. If you look up here, this thing is literally horrendous. I don't know. It was really bad. I used the auto rooting feature, which is super bad. But this is a better version. This is the goated version. That was the mid version. That was one of my troubles. My other trouble was my motors were super dysfunctional. One was way stronger than the other, so always at the end it would veer off to the end when I tried to steer. And my solution was just to not do that much and use IR correction instead. And then my last greatest trouble was my MOSFET footprint was wrong, and so I had to fully take them out and then do some surgery on them, and like it made it really annoying because they kept breaking off after my surgery, and so I keep resoldering them. Okay, for the future, these are my goals for next year after learning all the things that I learned. I want to make my mouse way smaller since my thing was like huge and it kept like hitting walls and stuff. And also like if it's smaller, then it's lighter and it can be faster. I want to make my PCB less clustered because when I was soldering on like capacitors, I had like a capacitor like zone and it was really bad because they kept like fusing and stuff like that and it was really annoying. And then I want to make my mouse look cooler as well. Someone has a question.
Yeah, would you switch to KeyCAD instead of using Eagle?
Yes, and we were using Eagle before, but now we're going to switch to KeyCAD because KeyCAD is better. KiCad. I think that's it.
Hi everyone, my name is Eric, and this is my teammate Johnny. We're talking about our mouse, which is the mouse, we called it mouse potato. And also, so actually first I'm going to talk about how to drive straight through the maze using IR correction. So there are two types of corrections that we'd like to make when we're driving through the maze. The first type is basically when you see an edge of a wall, you'll know how much further you need to go. And secondly, when you're driving alongside a wall, you can use that to correct for side-to-side errors. Okay, so here's a quick review of the hardware on the RAT. So as you can see, it has 4 IR sensors. Like this black and white pair there is one IR sensor pair. So 2 of the pairs face forward and 2 of them face to the left and to the right. We also have 2 motors and 2 encoders for precise movement, and the encoders allow us to know exactly what the angular positions of the wheels are, which helps with driving straight. And the sensors help with like correcting for errors that have sort of accumulated because they allow us to see where the walls actually are. Okay, so detecting wall edges. As you can see here, right now the RAT is going forward and the IR sensor is aligned with this edge in the wall. So what the robot would see is a transition from seeing no wall to a wall or vice versa. And when that transition happens, we know exactly how much further we have to go straight because we know how big the cells of the maze are. And the transition can also happen the other direction where you go from seeing a wall to seeing nothing. So how is this actually like implemented? Well, we just take the, so this drawing is perhaps what this drawing is what the sensor would see over time. So this rightmost square here is like the present, whereas the leftmost square is like 10 milliseconds ago or 9 milliseconds ago. So if the average of the most recent samples compares significantly differently from the average of that longer window, then we say we've detected an edge, and at that time we can update the remaining distance that we still have to travel. Okay, so the next type of correction, which is driving straight while going parallel to a wall. Basically, this is pretty straightforward if you can tell where you are. So I feel like a lot of you in the audience at the have taken IEEE 3 where you have to make a line following car, and this is basically the exact same idea. So if the left or the right IR sensor sees a wall, then we know what the IR sensor should read when the wall is at sort of the perfect distance. So we can just take the difference between the expected reading and the actual reading, and that would be our error. Except we also have to divide by this IR sensitivity term, which exists because the IR sensors are actually not equally sensitive. So what I mean by that is, so in this left picture where you can see the robot is directly centered, for some reason the left one reads 2100 and the right one reads 746. So yeah, I don't know what accounts for this big difference, but it'll be different for every robot. So here you can see that like when we shift the robot slightly, the left reading changes by 17, whereas the right reading changes by 6, or by 3, sorry. So we say, we can use that to figure out that the left sensor is about 6 times more sensitive than the right one. And so that's why in the expression here, we were dividing out by the sensitivity so that we sort of have a normalized error value. Yeah, and that's it. Here are some credits for where I got the images. And I took some of the pictures by myself too. So now Johnny's gonna talk about our hardware design, which unfortunately we did not compete with.
So, of course, Micromouse is just as much a software project as it is a hardware project. And as Eric introduced, I kind of led the design on the hardware side. We started from humble beginnings. Neither of us knew how to design a PCB. We're basically making this from scratch. So we started with a very small circuit, the one on your left. That's a linear voltage regulator that basically takes our voltage from the battery and puts it down to 3.3 volts, which can power a lot of our things like our sensors, our microcontroller. We also have a larger circuit on the right. That's our IR receiver and transmitter. A nice thing about KiCad, which is another of these CAD programs, is that they allow us to take these blocks and make them smaller and basically abstractify. So we don't have to think about individual components. We can make bigger circuits from smaller circuits. We went from chaos to order with the help of our leads. We went from giant spaghetti monster to slightly less of a spaghetti monster. We learned a lot about what's called ground plane stitching, because motors are really high current, so we're using both sides of the PCB, both sides of the conductor to conduct electricity, make sure that we can actually handle the amount of current we're putting through the motors. Finally, we were left with this. It's kind of hard to visualize how big this is, so I actually brought our PCB. Here it is. It's very small. We kind of flew a little too close to the sun this year. We did burn out, as Eric said, right before AAMC, so we're not able to compete with this. Luckily, we had the RAT, our sort of starter mouse, and we were able to recover. But hopefully next year we can continue working on this, refine it, and actually run it at AAMC. All right, that brings us to our final presenter for Micromouse.
Hey guys, I'm just going to talk super quickly about my Micromouse. I was Micromouse lead a couple years ago, and for fun, I've been making something that might look a little bit like something you've been seeing around campus. These little starship robots. These are the actual ones, the big ones here, but mine is sitting on top of there, and it actually is a functional Micromouse. So just to talk a little bit about the design here, yeah, it's just a really funny looking Micromouse. I 3D modeled all of the parts in Fusion 360, managed to figure out how Fusion has some software that allows you to work both with the PCB electronics designing side as well as the CAD side. So this was all in one program, which is kind of unique compared to other pieces of software. Let's see. Yeah, so you can see kind of all the internals in there. It has a funny shape because the motors are actually mounted to the bottom of the robot instead of to the top, which most other teams had. And that's mostly just so that it would look correct and fit right. So in terms of design considerations, I pretty much scaled the entire thing to the size of the wheels, which meant that we had a kind of a huge case for the size of a Micromouse maze, which means like turning and stuff, I'd have to be very precise in order to get it to like actually fit in the maze and not just run into the walls all the time. And it had a relatively small board here, so it was a little bit of a challenge getting everything in there, but luckily not too bad. The other important thing was to put lots of LEDs on it, have some RGB, and make it look cool, because that was 100% of the quality factor for this project. Winning the competition, not so much. But here's just a couple more cool photos. This is one of it in progress. You can kind of see how I'm like modeling against the real thing, trying to get it to be one-on-one. And then here's a quick photo of the finalized project, all 3D printed parts, everything screwed in. And it actually has 6 wheels in there, only 2 of which are actually driven. But yeah, super cool stuff. Oh, there's also an LED inside the flag, like the real ones. So try to make it as good as possible. But that's about it for me. You can come and look at it later, but I'll hand it over to our next SPIer.